Well, in this video, I'm still in cryptography, and I'm looking at RSA encoding and decoding. So we have a problem here, a practical problem. Suppose the RSA system is being used with a public key. So we have a public key that's published E, N, where N, that's the modulus part, is 187, and E, that's the exponents part, is 13. So we want to encrypt the message. Encrypt the message. So remember your encryption function. Your code is congruent to your message to the 13th power mod 187. So we want to encrypt 17. So here we go. I'm going to do some work here. I got C is congruent to 17 to the 13th power mod 187. Now if you try to do that in your ordinary calculator, if I try to do 17 to the 13th power, I'm going to get an overflow. So let's see, how big can we go with our regular calculator? 17 to the 8th power works. Let's see, 17 to the 9th power doesn't work. So I'm going to do 17 to the 8th. So I'm going to write it this way. I'm going to do 17, and we can do 8 plus 5 is 13. So since my calculator can handle 7 to the 8th, that's what I'm going to break it into 8 plus 5. 5 is smaller than 8, so we can handle 17 to the 5th as well. So I'm going to do 17 to the 8th times 17 to the 5th mod 187. I'm going to reduce 17 to the 8th mod 187 in my calculator, and then 17 to the 5th mod 187 in my calculator. Into my calculator, I'm going to take 17 to the 8th power is a really big number. It's like 6975757. 7441. I'm going to divide that by 187. I get a quotient of 373.03515. So I'm going to take 6975757 757,441 minus 187 times that quotient, 373.03515. You get a remainder of 136. So 17 to the 8th power looks like it's 136. Let's see, 17 to the 5th power. 17 to the 5th power. I'm going to take 17 to the 5th power. I'm going to get a really big number. I'm going to divide that number by 187. I'm going to get a quotient of 7592. I'm going to take 17 to the 5th power, which is 1419857. Subtract 187 times that quotient, 7592, and I get a remainder of 153. Now this is all mod 187, so what I need to do, I need to multiply the green numbers together here. 153 times 136, and I want to mod that by 20,808. So I'm going to take 20,808 divided by 187, quotient of 111, and I want to figure out my remainders. I'm going to take 20,808 minus 187 times 111. I get 51. 51. So that's how you can do that with a simple calculator. So here my code. So far I have 51 in place of 17. Now, there's a way that you can do this much more efficiently without using your calculator and having to break things up like we have here. You can go to a website I have here. Maybe you can see it's decode.fr. Decode.fr. And what I want to do a modular equation. A modular equation. So I'm going to set up here x equals, so we had what, 17? We're going to use the caret button. I don't know where that is exactly on this. It's the caret button that's raised to the 13th power. And we want to make sure that the modulus here is 187, and it is. And once we do that, we're going to hit the solve modular equation. And here on the left side, you see results processing. something blocked. Okay, let me try it again. Normally it doesn't do that. Okay, it wasn't doing that earlier. Looks like we have a... Okay, here it is. Right here, it's right. 17 to the 13th power. Mod 187 is 51, so your answer is 51. That's what we got. So that's an efficient way to do it. Okay, let's do the same thing for 19. So we're going to start with 19 to the 13th power and mod that by 187. Now, how big can I do 19 to what power? 19 to the 8th power is too big. My calculator can't handle it. 19 to the 7th power. Can my calculator handle 19 to the 7th power? Yeah. So I'm going to break this into 19 to the 7 plus 6 power. Mod 187. So I got, what, 19 to the 7th times 19 to the 6th that I can handle both of those. So I'm going to do 19 to the 7th first. I'm going to divide that by 187. I got to find the remainder, so I'm going to take 8, 9, 3, 8, 7, 1, 7, 3, 9 minus the quotient 4, 7, 8, 0, 0, 6, 2 times 187 to get the remainder there of 145. So 145 is the remainder when I do 19 to the 7th mod 187. Now we got to do 19 to the 6th. We're going to divide that by 187, get a quotient of 251582. So I'm going to take 4704, 5881 minus 25152 times 187 and get a remainder of 47. And I'll multiply 145 and 47 together and then mod those by, reduce those modulo 187. So let's see, 145 times 47 is 6815. I'm going to divide that by 187. Quotient of 36, so I'm going to take 6815 minus 36 times 187. And I get 83, it looks like. Assuming I plugged that in my calculator correctly, so 83 replaces 19. Let's check that in the online calculator here. So decode FR. So this time I had, what, 19 raised to the 13th power. And mod 187, I'm going to solve the modular equation here, hit that button, see our results here. Okay, so we got here 19 to the 13th power mod 187 is 83. And that's exactly what we had, right? Okay, so what do we want to do next? Number 2. So that's how you encode stuff with the encryption function using the public key. So what we want to do now is we want to find the private key. So the private key, determine the private key, is something that only the host has. And even though the public, the users, have the public key, they normally aren't able to find the private key. It's very difficult normally. But we're going to find the private key today because, well, we're geniuses. We're going to figure it out. Well, really the reason is because we're going to be dealing with, right, we have small numbers. 187 is a small number. So the key is that 187 is a small number. Normally you get these giant numbers, which makes it very almost impossible to discover what D is, the private key. So remember that N here was 187 and E was 13. Keep that in mind. Now, what we want to do, we want to find the P and the Q. What are the P and the Q? The P and the Q are the primes that N breaks up into. So I'm going to say, okay, what's the square root of 187? I'm going to floor that. Square root of 187. Is around 13, and we're going to floor that so we get 13. So let's see, any primes that divide N. Okay, 2 doesn't, 3 doesn't, 5 doesn't. What about 7? 187 divided by 7? No. 187 divided by 11? Yes, 11 times 17. So n is actually 11 times 17. So that's your P and your Q. Your P and your Q. So what we were able to do just now is factor into 2 primes. That's why normally you can't crack the private key. Nobody can find the private key, is because people can't factor into primes. Now, it was easy for us to factor into 2 primes because we had a small number. But imagine a number that was millions of digits long or billions of digits long that's made up of 2 primes. Well, then you have to find these enormous, enormous prime numbers, a P and a Q, and that's almost impossible to find. And that's why that's the step at which most people, if they were to try to find the private key, they would fail. They wouldn't be able to find the 2 primes. So we did the impossible, right? We found the 2 primes, but only because it's not impossible here, right? It's a really small number. 187 is a really small number. So that's the hardest part, factoring into primes. Okay, so here our P is 11 and our Q is 17. So what we want to do, we want to find D. What is D? Well, D is E inverse mod P minus 1, Q minus 1. In other words, we're talking about 13's inverse. Mod, well, P minus 1 is 10 times Q minus 1 is 16, so mod 160. So we're talking about 13's inverse mod 160. So that's what I got to do to find the private key. I got to find the inverse of 13 mod 160. So here we go. We're going to write 13 times C is congruent to 1 mod 160. So we got to solve this congruence, right? That's how you find the inverse. Oh, this is a D. Let's call it a D. Rather than a C, let's call it a D. That's what D is. 13 times D is congruent to 1 mod 60. So how could I do that? Well, I could start with the Euclidean algorithm here. I could take 160 and divide 13 into it. Let's see, 160 divided by 13 has a quotient of 12. 160 minus 12 times 13, the remainder there is 4. This is doing the Euclidean algorithm. Okay, now I'm going to take 13 and divide 4 into it. And that's going to go 3 times, and it's going to have a remainder of 1. Then we take 4 and divide 1 into it. That's going to have a quotient of 4, a remainder of 0. So we're done with the Euclidean algorithm. Our last positive remainder was 1, so the GCD is 1 here. And we're going to write that as 1 is 13 minus 3 times 4. And then we got to update one of the numbers, either the underline 13 or the underline 4. We're going to update the underline 4 here with 160 minus 12 times 13. So I got what? 13 minus 3 times 160 minus 12 times 13. All that's equal to 1. So cleaning that up, I got 13 minus 3 times 160. Negative 3 times negative 12 is positive 36. Times 13 equals 1. Remember, this 13 in front has a 1 in front of it, so that's going to be 3713. So I got minus, well, let's do it this way. Let's write it this way. 13 times 37. I write it like this. Right, it's combining these together. The 1 and 36 is 37. Minus 160 times 3 equals 1. So what I'll do, I'll get the 13 by 37 by itself, 13 times 37 by itself. I'll take the 163 to the other side, so I got 160 times 3 to the other side plus 1. And if you think about this statement, this is the same statement as 13 times 37 is congruent to 1 mod 160. So that means that the D here is 37. So the inverse of 13 mod 160 is 37, so D is 37. So that's the private key, So that's the one that's pretty much impossible for people to crack. They can't find the private key, and it all comes back to being able to factor that n into 2 primes. Now, we were able to factor n here into 2 primes because it was a small number, 187. Okay, now let's go into step 3. We want to learn how to decrypt the encoded data. So I want to decrypt 15 and then 5. Now what are we going to use? We're going to use our decryption key. Our decryption key, or our private key, is 37. That's the one the host always has. So the function for decryption is the message is congruent to the code to the dth power mod n. So in our case, it's going to be the message is congruent to the code to the 37th power mod n. What was n? It was 187. So our message here well, let's go ahead and work through this first. I'm going to cheat, okay? I'm going to cheat. So I want to find 15, the message for 15. So I'm going to plug in 15 for my code, raise it to the 37th power, and mod that by 187. I'm just going to cheat. I'm going to use the cheating calculator. So here comes the cheating calculator. Where is it? There it is. Okay. So I'm plugging in 15. I'm going to raise it with a caret to the 37 power. I'll make sure my modulus is 187. It is. And we're going to solve. And we'll probably get a pop-up on this machine. This iPad gets pop-ups a lot, it seems now. So we're getting x here reduces to 104. We get 104. So also we're going to do 5. We're going to do 5 to the 37 power mod 187. So we need to reduce that mod 187 5 to the 37 power. Let's see, can we type it in? Where's the caret? The 37 power. Okay, solve modular equation. We're going to tap that. And it looks like 14 is the answer. 14. So we're going to have 14 here. So my message here, what I've decrypted, we have what, 104 and 14. All right, that's all we're going to really do with RSA. There's a lot more you could do with this, but yeah, we want to just show you the basics, the underlying principle, and